Hi again, everybody. So, moving right along, we are on Chapter 3, Section 4, Components of a Vector and Unit Vectors. So, I just want to highlight, as I kind of said from, I'm already at the bottom of the chapter, as I said from the last chapter here, this is kind of where we're really going to get into stuff. Um, the graphical method of adding vectors is not recommended whenever high accuracy is required or in three-dimensional problems. So as we kind of talked about, as I kind of brought this up in the last section, like I said, it's high accuracy. I feel like is always required. I mean, in terms of doing if we're taking the time to do calculations, I would consider that high accuracy. Low accuracy would be like eyeballing something and saying, "Hey, that looks okay," which we're not going to do too often, right? Um, Usually what we're going to do here is, as it says in the bottom of that paragraph, we're going to break these up into components, right? So let's get into this. Oh, I'm still in highlighter mode. Let's get into this and take a look at what we have here. Actually, I want to bring this down because I would like to insert some axes. Here we go. All right. So here is our traditional XY plane. There's our x-axis. As I mentioned, you guys have probably, I mean, you've seen a few of these videos now already. You noticed I try to be super consistent. I always put my arrows, even when I just draw a rough sketch for an axis, I always label the axes X and Y. It's important to always, just get into the habit of always doing these things. Um, like I said, I'm going to try to always do it. If I forget every once in a while, but I'm usually pretty consistent with making this appropriate axes. It sounds weird. All right, anyway. So what we have, we're getting pretty used to some vectors, right? Oh, let me try to do that a little bit better. I forgot the fancy vector thing I can do. Squiggle. There we go. So we have here a vector. All right, let's call it vector A. Very interesting naming convention here. So how we're going to do it in most cases, doing this, is we're going to break this up into what we call its component vectors. There's a multitude of reasons for this. The biggest is most of our problems we're going to be dealing with, two dimensions, and it's going to be our x and y axes, right? They're not always going to look, vertical and horizontal like this. Sometimes they'll be rotated, like our xy plane, just for example, could look like this, This could be our x-axis, and this could be our y-axis. Like if we're dealing with a problem where something's on a hill, right? If we're going up a hill like this, maybe this is what our axes look like. They don't actually look regular up and down, but we're still going to break them up into two perpendicular axes, an x-axis and a y-axis. So that's kind of what we're looking at here. So I'm just going to ditch this for now. But that's kind of what we're thinking. So we have this vector A here. What we mean by breaking up into its vector or its components, its rectangular components, however they want to call it, is we're gonna do. It's called, if you've taken some more mathematical classes, where you get into like heavy vector stuff. If you haven't done it, you'll eventually get into it. I want to say it's multivariable calculus, but I can't exactly remember. But you'll hear of the projection of a vector along another vector or just about something. So what our components are, what they really are, is they're a projection of vector A about the axes. So I forgot to do that the right way again. So if we have vector A here, let's say this would be rough. That's pretty close. That's going to be a x. And then in this direction, we would have AY. So what AY is and what AX are, they are the projections of vector A about the y-axis and about the x-axis. So this is technically, I think this is the more appropriate way they're drawn, with the tips all starting from the same locations, like with the y and the x going out. The way I generally draw them, and I feel like how you'll see them more often, is you'll see, oh, it doesn't work. Control maybe? Nope. Shift? I thought I just hit shift. Nope, it doesn't work either. All right. Just try that. There we go. I feel like what you'll see more often is, and this is kind of how I do it more often, is I draw it like a triangle, because that's what you're going to be dealing with. So I'll usually draw it kind of more like that. Oh man, I'm just killing myself over here. So I'll usually draw it more like that. like in the triangular method. Either way is fine. Whatever you're used to is perfectly fine. Both of these are acceptable. As we've talked about before from from section 1, maybe 2, right? It doesn't matter where the vector is in space. If it has the same magnitude and direction, it's equivalent, right? So AY here and AY here are both the same vector. Even though they technically don't start from the same point, they are the same vector. So that's how we graphically break it up into its XY components. And then finding the values of these, AX and AY, is just, I guess I was going to say basic algebra, but I guess it's trigonometry, right? Where's my cursor? There we go. In order to be able to accomplish this, we would need to know some stuff, right? We would need to know the value of vector A, or the magnitude of vector A, and then we would also need to know our angle theta here. We would need to know that to calculate it. But after that, it's just algebra. Whoa. Let's go back to my red here. So if we have a value of vector A and we have a tangent theta, or excuse me, I feel like I did that in the last section too. We have an angle theta. We can find what AY and AX are just by, as I said, using trigonometry. So if we're just dealing with technically we're just going to be dealing with the magnitude. So I'm just not going to use the vector hat, or the vector line notation above. So AY would be equal to the value of vector A times vector Y is the sine of theta, right? Because we know sine theta is equal to opposite over hypotenuse, and in this case the opposite is AY and the hypotenuse is A. So if we're solving for AY, ta-da, we end up over here. And same logic for AX, it would be equal to A cosine theta. So some things to keep in mind here. AY and AX will not always be A sine theta and A cosine theta. If all of a sudden, if I give you this angle, and let's say I give you the angle theta along the vertical axis, these get reversed, right? So this is just my, overall mathematical scientific feel. Don't memorize equations. Understand how the equations are, where they come from, how they were found, and then apply them, right? So the A sine theta and A cosine theta are assuming your theta is about the horizontal axis, right? The adjacent angle, or the adjacent line, is your x component. If your adjacent line is the y component, the AY vector, the AY component vector would be A cosine theta. So you always have to keep track of that, because there'll be problems. There'll definitely be problems where it'll say, vector A is 53 degrees from the vertical, right? So if it doesn't say anything, if it's just a text problem, doesn't say anything, there's no image associated with it, you should pretty much always assume it's from the horizontal. But if it explicitly says from the vertical, or, contextually, like a nautical problem, like east of north, would be from the vertical, or if there's an image and the angle's given from the vertical. And once again, mathematically, right, it makes sense, because we know these angles are complementary angles. Complementary or supplementary? Whichever one means they add up to 90, right? Theta yellow and theta orange here. So obviously the sine of theta yellow is equal to cosine of theta orange, right? That's just, once again, mathematics. But anyway, yeah, so this is how we come up with the magnitudes of each of these vectors. And we break these guys up. The nice thing about this is there's no angles defined, because we know the angles of AX and AY, right? AX is in the horizontal direction, so you could say 0 degrees. AY is in the vertical direction, 90 degrees. Depending on if they're negative, right? You might say AX is 180 degrees, AY is 270 degrees. You could say that, but they're straight up and down, straight left and right. So that's the benefit of that. You don't have to worry about any angles there, because you were given the angle of theta. Here's pretty much what I just said. It's a little nicer drawings, right? My drawings are probably crap there, but but you can see the angle theta is given about the horizontal. You can draw AY in either location, kind of wherever you like it, and then they just kind of connected the dots, the little dotted lines there, to show where everything else is. But same stuff. So I said, we're given A, so we don't have to worry about finding the angles for AY and AX. However, the way these problems usually work is you break a vector up into its components. You're going to do a bunch of stuff to it, maybe add vectors, subtract vectors, multiply vectors in the future. But we're going to, manipulate these vectors in a bunch of ways, and then we're going to be left with these resultant component vectors, right? And then we are going to have to put them back, we are going to have to put them back into a singular vector. So let's say, we're given a problem. Grab my axes again here. Oh, excuse me. Oh, still in yellow there. That's okay. We'll deal. So x, y. Let's go back to red. Okay. So let's say in this case now, we did some work. We found our component vectors. Here is my vector. I'm going to call it resultant. So we're saying. So here's my resultant vector y in the y direction. And here is my resultant vector, and that should be vector notation there, or my resultant vector in the x direction. So I have these two resultants, and what I want to know is I have my resultant components. I want to know what my resultant vector is. Oh, I didn't get the cool little arrow that time. That's okay. So there is my resultant vector, right? I need to know what r is. So let's say I have rx and I have ry. I have my two resultants, but I need to come up with what my actual r value is. So there's my theta. So once again, basic arithmetic, not arithmetic, I guess algebra, trigonometry, that whole deal. So rx, ry. Another way to, if we wanted to label ry, we could label ry is up here. This is ry as well, same thing. Arrow on there. If we did want to calculate this, it's the same triangle stuff. So to find theta, right, it's going to be the inverse tangent of ry over rx. Notice I'm not using the vector notation there because it is just the magnitudes of those values, right? And once again, as I've said before, if the angle was given with the vertical, these would be reversed, but just always pay attention. You guys will never make that mistake, I know. So then if we wanted to come up with the magnitude of vector r, it's just good old Pythagorean theorem. So it's going to be the square root of rx squared plus ry squared. Ta-da! That's it. So this, then we would go back, and then this would be our resultant vector at a given angle. So the vector would have a magnitude of this and an angle of this, right? Magnitude here, angle here. Ta-da! Isn't that cool? Here's a nice figure that kind of just breaks up how the components are going to go depending on how your vector is. If you have a vector in the first quadrant, ax is going to be positive, ay is going to be positive. If you're in the fourth quadrant, ax is going to be positive, ay is going to be negative. I don't think this is going to be groundbreaking for anyone. Just if you need a quick refresher in terms of quadrants, first, second, third, fourth. I don't know why they're always in Roman numerals, but they just always are. I guess because you don't want to have like random numbers floating around a coordinate plane. That could be probably confusing. But those are your components, and that'll show how those are your quadrants, and this will show how your components are broken up depending on which quadrant your vector is in. So the dark red are the vectors, and the kind of the pinkish orangey light red are the component vectors. Okay, so the next thing we're going to talk about is unit vectors. Unit vectors. So what a unit vector is a unit vector is a vector with a magnitude of 1 in any given direction. So that's it. A magnitude 1 in any direction. The unit vectors we'll commonly use are going to be along our axes, right? So we're going to have, busting out the three-dimensional line. Look at that. So we have our x-axis here. I'm going to call this our y, and I'm going to call this our z. Z's going up there. Depending on how you look at this, you could go either way, but I'm just going to call them this way. So what our unit vectors are, I did that again. They're going to be, there are 3 vectors along each of the positive axes. So I'm going to call these my positive axes. I'm trying to draw these roughly the same size. I don't know how well I did there. Y looks a little bit bigger. But these are our unit vectors, in the x, y, and z directions, and they're given the nomenclature I, j, and k with these little carrots on top of them called hats. The reason for this is just to easily break up to a way to easily write vectors. So if we did have a vector a, let's say let me make up a vector a here. So let's say we have a vector a that has an x component. Let's say vector a has an x component of 4, or x magnitude of 4, a y magnitude of 5, and a z magnitude of 3. That's these are its component vectors magnitudes. So the way you would write that in unit vector notation is what you would say is vector a is equal to 4 I hat plus, what I say, 5 j hat plus 3 k hat. It's just an easy way to, in one line, write all the values of the component vectors. Because before, like when we were up here, we talked about, ry, the vector ry, magnitude ry, vector rx. You don't want to have to write for every vector, vector a, x magnitude, y magnitude, z magnitude, whatever. So this notation shows it's just a nice, easy way to write it, because what this represents is 4 is a scalar quantity, right? And I is a unit vector, so it's a vector of 1 in the x direction. So we did scalar vector multiplication in the last section. So when you take the scalar quantity 4 and multiply it by unit vector I, which is a vector with a magnitude of 1 in the x direction, you end up with a vector of 4 in the x direction with a magnitude of 4 in the x direction. And just like the 5j and 3k. So it's all the same. This is pretty standard. I don't think I've seen this really done any other way. The hats kind of might look differently from textbook to textbook, website to website, but it's pretty standard. So, yeah, I mean the big thing is to just you don't really have to use these very often. They basically become like units. Like this is just the x component unit, y component unit, k z component unit. That's essentially what they're telling you. But I mean, having an understanding of what's happening, I'm big on that, right? And here's a textbook, a little bit more clean sketch of kind of what I've drawn there. So you have your I, j, and k, hat unit vectors, and then there's an example of a vector a broken up into its ay component j, ax component I. So that's just, like I said, a cleaner version of this. So the reason we do all this, breaking vectors up into components and all that, kind of going back to the last section with the vector addition, I kind of said the graphical method is kind of wonky, you're never really going to use it. So what we're going to do is we have two vectors, right? And we want to add vector A plus vector B. I feel like I wrote that like a bunch last time, right? And we want to come up with this vector R. So the resultant vector, what vector R is going to be equal to? It's going to be equal to the AX plus BX I, and then we'll just say 2 dimensions for now, plus AY plus BY J hat. So there you go. So you can kind of see how easy this becomes once you break it up into components. So you're given these two vectors A and B, you break them up into their component vectors to find the vector quantities for R. So the X, if we break this down, what this is saying is the magnitude in the X direction of the resultant vector is the sum of the magnitudes in the X direction of the two vectors. And same logic, the magnitude in the Y direction of the resultant vector is going to be the sum of the Y components of the vectors you're adding together. So AY plus BY, AX plus BX. And if we take a look at this graphically real quick, kind of like from what we did in the last section, it makes sense, right? I talked about how we're never going to really graph things. We're never really going to add and subtract things graphically because it doesn't really make sense. But just take a, I don't want to do that. There we go. Just take a look at this for a second. Even how when we did things graphically, like we had vector A. Oh, it's something pretty simple. I'll keep going in the same direction even, right? I think this will make it even easier to visualize. And we have vector B here. And then we know from the last section that the resultant vector, that might not work. Oh, that did work. Wow. It's gonna look like that, right? That's gonna be our resultant vector. And if you guys followed along with the textbook example, you could use, this is a non-right triangle. So you could use law of sines, law of cosines, as long as enough information was given about this and figure out what your resultant vector is. But if we take a look at this logically for a second, so here is what A, come on, do it. Oh, it didn't do it. Oh man, I lost my touch. It's over. There we go. So here's what A is broken up into, right? Here's AX and AY. And here is BX. That one, I didn't think that was going to work. Oh, wow. Okay, I should keep trying. And here is BX and BY. Right? And if we take a look at the resultant vector for R, right, it's going to be roughly like this. So there's my R, oh, that's RX. There's my RX and my RY. So if we take a look, RY is literally composed of AY plus BY, right? I'm just talking magnitudes here. RY is equal to AY plus BY. And you guessed it, Rx, if we look in the x direction, AX plus BX, AX plus BX equals Rx. So that's where all this comes from. And the same thing would work, if you were going backwards. BX, if BX were negative, it would obviously subtract the value, or vice versa, all that jazz, right? The same stuff applies. Subtraction is the same as adding a negative. That whole part. But so what you're going to see a lot of these problems, especially if you're just learning this for the first time, or maybe just the first time in a long time, the general gist of a problem is you're going to get a vector, you're going to break it up into its components, you're going to do some stuff with it, and then you're going to put it back into a resultant vector. That's kind of I really hope you enjoy doing that, because you're going to be doing it quite a bit in this course. So let's get into it, and let's check out an example problem or two. All right, let's start off with this one right here. Super straightforward, not a trick question. Just add the vectors, right? Find the sum of two vectors A and B lying on the xy plane and given by blah 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 blah. All right. So if we want to find go back to my red here, we want to find this resultant vector. All right, find the sum of the two vectors, right? Oh, it doesn't even say. It just says find the sum. It doesn't even say what if they want the resultant or not. I guess not. I'm going to assume no. Right, so our resultant vector, it's going to be, in this case, 2.0, because that's coming from right here. I guess they're both 2.0. Plus, there's a lot of 2.0s here. 2.0 right there. And that's going to be my I. Plus, another 2.0, kind of annoying. That's coming from right there. And then plus, or you could plus -4, or just do minus 4.0. And that's coming from right there. There's a lot of crossing lines there. I hope that's okay. J hat. Make these a little bit more clear. This I is coming from here, and this is coming from here. Probably could use my arrows there, but that's fine. So then you would just literally do some arithmetic here. So 2 plus 2 is going to be 4. 0.0, let's keep the sig figs, 4.0 I hat, and then over here plus, you could say plus negative, I'm going to just write it as negative, minus 2.0 J hat, right? And that's really it. It's not a trick. You just add the components, boom, there's your new vector. So if we want to look at it, if we want to, let's sketch this just to take a look at what we're looking at here. So if here's our components, X and Y. So if I were to draw A, so A is 2 plus 2. So A is going to be just pretty much a 45-degree angle here. Oh, okay, I learned something there. So there's my AX, and this is roughly, or not AX, excuse me, there's my vector, that's just my vector A, and then vector B is what? 2, positive 2, negative 4. So it's going to be still over 2, but then -4. So it's going to be something like that, right? So there's my vector B. And what we came up with was for our resultant vector. Oh, sorry. If we're doing tip to tail, if we're going to represent adding this graphically, let me actually do this how we would do it. We would do tip to tail, right? So we would put that there like that. And then our resultant vector would be from the origin to here. So that would be my resultant vector. Why did I write Y? That would be my resultant vector. So you can see graphically, I think we're pretty much, we look like, if I had to, like I said, if I was doing this problem graphically, I looked at that, I said, yeah, we should be, 3 to 5 in the X, a little bit in the negative. Obviously, resolving this into its components, you can see pretty quickly where we end up, but that's just visually what we're kind of doing, what we're doing right here. So I guess let's just take this a step further and let's actually find what our, this is the unit vector notation. Let's find our vector notation for what R is going to be. So if we want to find the magnitude of R, go back to red. If we want to find the magnitude of R, right, we know the magnitude of R is going to be equal to the square root. I'm going to go a little shorthand here, 4 squared plus 2 squared. I know -2 squared, but right, with the negatives, it doesn't matter. Magnitude, direction doesn't matter. It's magnitude. But anyway, what we got here? We got 16 so root 20. Let's see here. Square root. Where is the square root on this thing? I don't know. 20 to the 0.5. Oh, what the heck? Escape, clear. Let's try this again. What? Do I have like my lock on or something? There we go. 20 to the 0.5. 4.47. So my magnitude of R, I lost it, is 4.47. And then if I want to try to figure out what my angle is, I'm going to say, let's say, so if I wanted to do this, the way this R looks is we have 4, and then down 2, and then there's my nice little triangle, right? And I'm trying to figure out what this theta value is, and this value is 4, and this value is 2. So theta is going to be equal to the inverse tan of what? 1/2, opposite over adjacent, right? Yeah. Let's go back over here. Let's see here. I'm probably in radian mode, aren't I? Did I get the alpha? No. Alpha. Tan. What? Second alpha? There we go. Once again, a 0.5. And then so we find, that's definitely radians. Let's, yeah. Ta-da, degree. Okay. Let's try that one again. What? I guess I didn't save that. Change. My bad. Enter. Enter has to save. Okay. There we go. So what we find is theta is equal to 26. I would say 26.6. Right? So theta equals 26.6. Now, degrees. So keep in mind, that is, if we look back at our axes here, what we found was we found the angle below the horizontal, right? This theta here corresponds with that on our Cartesian plane. That's not how you want to do vector notation, right? We always want to go counterclockwise from the positive x-axis. So in order to find that, I mean, it's just 360 minus that. So answer minus 360. So 333.4. So my theta, so my vector R is going to be 4.47 at 333.4 degrees. So that is how you would do that. Alrighty, let's take a look at one more example, and then I think we'll call it a lecture here. All right. Example 3.5, taking a hike. A hiker begins a trip by first walking 25 kilometers southeast from her car. She stops, sets up her tent for the night. On the the second day, she walks 40 kilometers in a direction 60 degrees north of east, at which point she discovers a forest ranger's tower. Determine the components of the hiker's displacement for each day. Determine the components of the hiker's resultant displacement for the trip. Find the expression for r in terms of unit vectors. Okay, that's convenient. So that's a less of a step we have to do there at the end. But all right, let's get into it. First things first. As always, let's draw a picture because we love drawing pictures, right? I do. I know you guys do too. All right. So let's see. Oh, sorry about that. So we got our x-axis, we got our y-axis. I think for this one, I think it looks like we're going southeast in the beginning, so we'll go a little bit. In the negative. So let me just take a look. So 25 kilometers southeast from our car. So southeast, they don't give an angle, so I'm going to assume just from the text that southeast is going to mean a 45-degree angle. So they're not saying, like a certain number south of east or anything like that. So I'm just going to assume straight southeast is 45. So, I can change the color afterwards. Can I? There we go. Why I don't have all my other recent colors? Why are they giving me all these wonky colors? Whatever. It's just so. All right. So southeast, I'm gonna try to draw. That looks pretty good actually. And then on the second day, she walks 40 kilometers in a direction 60 degrees north of east. So north of east, that'll be from the horizontal. At which point she discovers the forest ranger station. So. I'm going to say 40, that's 60 degrees above the horizontal. I'm going to go with that. I'm just going to say that. I'm going to call it that. So we'll call this, I don't want to use 1, so we'll go with the classic vector A and vector B. We can draw in the resultant now. I know it's technically not what they're looking for until part B, but... Oh, man. Let's try again. I guess. All right, sorry, I'm just making myself laugh here. There we go. There's my vector. Okay, so that's gonna be my resultant vector there. We don't really need to worry about that now. For part A, it's just asking us to determine the components of the hiker's displacement for each day. So let's fill in some information we know here. So we know vector A has a 45-degree angle there, and then we also know that vector B forms a 60-degree angle there. Right, like I said, 45 comes from the term southeast. I'm just assuming that to mean straight 45, and then the following term is 65 north of east. So east would be to the right, right? You assume north, east, southwest. East is to the right, north is up. So north of east would be east, 60 degrees north. So 60 degrees rotation from north. So there's my two angles. So if we want to start looking at these component vectors for these two, this is gonna be. I didn't do the triangle thing. I don't know if this is beginning to know and wonder if this is worth it. So there's my AX and my AY, and then in the B direction, we will have. Maybe I should get better at it. BY and BX. So, once again, A is nice. It's a 45-degree angle, so it literally doesn't matter which one you do. AX and AY are going to be equal because, like I said, it's a 45. So you can kind of cheat a little bit there if you want. So AX is going to be equal to AY, which is going to be equal to the magnitude of A is 25 kilometers. So it's going to just be not 2.5, 25 km times cosine or sine, your choice, of 45. So let's see what that works out to be. So 25 times the cosine of 45. 25 times. Oh, whoa, geez, man, I'm all over the place. Escape. Clear. 25. What? I must have my locks on again. Clear. Escape. Clear. Let's try. Nope, that's still doing it. There we go. 25 times sine or cosine, doesn't really matter. Now I actually need to do that. Third time's a charm, right? Or 17th time's a charm. Cosine of 45. And yeah, okay, all right, I got you. I'll close the parenthesis. And then let's do, I just wanted the abbreviated answer, 17.7. So 17.7 kilometers, because we're just looking at magnitudes for these. So that's nice. Like I said, AX and AY are going to be equivalent. Don't need to do any extra work there. For BX and BY, obviously, that's going to be a different story. So if we work on BX first, so BX, it is going to be it's the adjacent angle. So it is going to be my magnitude times, so we have 40 km, and it is going to be my magnitude times my cosine. So in this case, my cosine is 60 degrees. So 40 times cosine of 60. So why does every time I leave it and it comes back, it's on lock? It's so weird. 40 times cosine. I did inverse cosine. I'm so bad at this. 40 times second cosine of 60. I'm going to close my parenthesis this time at least. Wow, an even 20. Look at that. Oh, yeah. I guess, yeah. Cosine is 60. So it's a nice even 20 kilometers. And then scroll down a little bit. So then we're calculating BY. So BY is going to be, once again, that same 40 kilometers. In this case, times the sine of 60. And if we calculate that, clear. It's still, why is it? I gotta look into this. Why it's always doing this every time I go to a different screen. Escape. Clear. All right. It's not 25 this time. Now it's 40 times the sine of 60. And that would equal 34.64. So 34.64 kilometers. So to figure out what R is now, we go back and we just look at the magnitude of R is going to be equal to the sum of the x's. I don't want to write it like that. That's too weird, right? Just so in this case specifically, AX plus BX I hat, and they did ask for it in unit vector notation, so this is consistent, plus B, or well, let's once again be consistent, AY. We're getting so close to the end, guys. I'm checked out. I'm just kidding. K hat, okay, or J hat. Jeez. All right, so let's see what we got here. Let's write this out. So AX, they're both 17.7 km plus BX is 20 km. That's going to be my I, and then AY once again 17.7 kilometers plus 34.64 kilometers J hat. So I definitely messed this up one. I definitely have a mistake here. If anyone can jump in now, I guess I'm not really lecturing live, so there's no point. But if anybody has been screaming this whole time for the last 5 minutes, like, you're doing it wrong, you idiot, you are correct. So I forgot that the AX value is going to be in the negative direction. So technically they're not equal. They do have the same that's cool. They do have the same magnitudes, but I guess technically they're not even the same magnitudes, because magnitude it's a quantity. It can be a negative quantity. So AX is equal to negative 17.7 kilometers. So that's my bad. See, we all make mistakes. It's all good. But luckily, later on down the road, when I eventually started looking at this and figuring stuff out, I'm like, wait a minute, that's not going to make sense for my resultant vector, because it doesn't make any sense. And geez, you guys are, I'm really not good at doing this unchecked. These should be obviously reversed here. That's AY and that's AX, right? So this should be backwards too. It's getting late, guys. It's getting late here. So AX is positive, AY is negative. There we go. Now we're on the same page, right? So the only like I said, it doesn't really change too much. Just the only thing that trickles down here is this value right here, AY, becomes a negative value. So All right, let's write this out. So our vector, and this is in vector notation. It's in unit vector notation, so I could have the vector there. So let's see what we have here. 17. So what's that just going to be? 37.7 kilometers I. And then plus, I guess, what, 17 minus, I don't want to do that. Let's bust out the calculator there. So we've got clear, second. All right, so negative 17.7. Oh, just minus second answer, right? Yeah, second. Ta-da! Oh, I did minus. Jeez, I'm the worst at this. 34.64 minus 17.7. 16.9. I'm just going to call it 16.9. So 16.9 kilometers J. Ta-da! All right, I think, did we answer our question here? So determine the components of the hiker's displacement for each day. So that's going to be our orange up here, right? There's our AY, there's our AX, there's our BX, there's our BY. Obviously, AY is negative. And then part B was determine the components of the hiker's resultant displacement for the trip. Find an expression for R in terms of unit vectors. So here is the unit vector. I wonder how you can do it. You probably, there's got to be a way to, I wonder if it would snap a square if I do a square really crappily. Oh, it will. Oh, and it gets, that's cool. All right. So there's my resultant vector there. So, alrighty. This was, I know, the longest one, but it was also definitely the most important one. So thanks for sticking along, for sticking in there. And yeah, thanks. See you guys later.